Today we cover the topic of matrix operations. The sums and scalar multiplication of matrices have been covered earlier, and now comes matrix multiplication. The need and the motivation for this topic will be clarified only later. The sums and scalar multiplication, we should review those also. The important thing about these operations that these are entry by entry operations, and it means that the sizes of the matrices that we want to work with must be of the same size. So we can add and subtract matrices of the same size, like a 3 by 2 matrix and another 3 by 2 matrix. Now, of course, we can scalar multiply any matrix with any scalar. So for example, in this example, we scalar multiply the 3 by 2 matrix with 5, and then we subtract from this the 3 by 2 matrix, which is 3 times this 3 by 2 matrix. So everything is done entry by entry. We scalar multiply the 1 entry, 5 times 3, 15, and then we subtract from this the other 1 entry from the other matrix, which is 3 by 2, so we subtract 6. Similarly, the 2 entry, 5 times 2, 10, minus 3 times minus 4 is plus 12. So 10 plus 12. Then the 3 entry, 5 times 7, 35, minus 3 times 1, minus 3. And so on. And then, of course, we have to do these operations to get the actual numbers. So don't forget to scalar multiply each entry in the matrix and also to subtract each entry from each entry. The new topic really today is matrix multiplication, and the very first thing to memorize immediately that the matrix multiplication is not entry by entry. It's a more complicated operation. And the definition is excellent for writing a numerical code, but it's not so good for calculations made on paper by hand. But anyway, we have to write down the definition and we have to understand how it works. So if A is a M by P matrix and B is a P by N matrix, which means that the number of columns in the first and the number of rows in the second are the same, then the matrix multiplication A times B is defined, and also it's defined as a matrix C, which has size M by N, the number of rows coming from the first matrix and the number of columns from the second matrix. And the Ig entry in this product matrix is the sum of the following products: AI1 times B1j plus AI2 times B2j plus, and so on, AIP times BPJ. Or writing it using the sum notation, the sum as k goes from 1 to p, the product AIK times BKJ. So note that the row indices I match the row index of C from the elements of A matrix, and the second column index of the B matrix matches the column index of the C matrix. And then if we have two matrices where the inner dimensions, so the second dimension of the first and the first dimension of the second, are not the same, if you have M by S matrix and R times N matrix, and S is not equal to R, then the matrix product A times B is undefined. So we cannot always multiply together all kinds of matrices. Here is the mechanics for the matrix multiplication. If you look at this summation, what you should notice that once you write the A and B matrices next to each other, then the A's AI1, AI2, AIP. These are the elements in the ith row of the A matrix. For if you want to calculate the ith row element of the new matrix, the product matrix. And B's, Bkj, as k goes from 1 to p, these are the elements of the B matrix in the jth column. So the ij entry for the product matrix comes from the ith column, ith row of the A matrix and the jth column of the B matrix. And this row and column, entry by entry, are multiplied together, and then the results are added together. For example, if we have this 2 by 3 matrix and a 3 by 2 matrix, then we can multiply these together because the 3 and the 3 are matching. The number of columns in the first and the number of rows in the second match. And then the definition says that it will be a 2 by 2 matrix at the end. And the way we get the 1, 1 entry in this new matrix, that this is the first row and the second, first row and the first column. So first row from the first column from the second, multiplied entry by entry. So it's 2 times minus 1, minus 3 times 5, and 0 times 7. Then this is, for example, the 2, 1 entry. So this comes from the second row and the first column. 5 times minus 1, 1 times 5, 4 times 7. And then we add these together. Then the 1, 2 entry comes from the first row, second column. So that's 2 times 0, minus 3 times minus 2, and 0 times 3. Finally, the 2, 2 entry comes from the row 2 and column 2. So it's 5 times 0, plus 1 times minus 2, plus 4 times 3. And then once we do these simple operations, we get minus 17, 6, 28, 10, 2 by 2 matrix. We can also now multiply together matrices and vectors, because a vector is just an n by 1 matrix, a special matrix with 1 column. So if the number of rows match here the number of columns, because we have 2, 2, then this is a multiplication that we can do, and the result will be a 2 by 1 matrix, which is actually a column vector again. So in the 2 by 1 matrix, the first 1, 1 entry is the first row, first column, 4 times 1 plus 5 times 2, that's 4 plus 10. And then the 2, 1 entry is the 2 row, the second row, and the first column. So it's minus 3, minus 12. And then we get 14 and minus 15 from here. And then if you look at this multiplication and also the result, now you can see that a linear system AB, where B is the right-hand side vector, can be written as a matrix equation A times X equals B, where X is an unknown vector that we are looking for, and that will be the solution. Another thing we can notice from here, from this operation, this multiplication operation, is that if we write A as a matrix built from the column vectors of the A matrix, denoted by A1, A2, and AN vectors, and then we have this X vector, the column vector, then when you multiply together A and X, the A matrix with the X vector, what you get is the A1 column vector times x1 plus and so on up to the ANth column vector times xn, which means that this is a linear combination of the columns in the matrix A. Some properties of matrix multiplication. Very important property. The matrix multiplication is not commutative, which means in general A times B equals B times A. Now sometimes they are equal, but usually they are not. So you have to be careful. So that means that it makes a difference whether you multiply from the left or from the right. Usually then we say left multiplication or right multiplication. And the next property is the distributive property of matrix multiplication over matrix additions. So we can distribute, if you have a parenthesis around B plus C, and we multiply by A, we can distribute this multiplication to get A times B and A times C. This was multiplication by A from the left. We can also multiply with A from the right. And again, we have the same property, this distributive property. We get B times A plus C times A. Very important, you have to keep the order. First B and then A, first C and then A. Next property is the associative property of matrix multiplication, which means that it doesn't matter how you group them into pairs when you want to multiply together three matrices. And then as a generalization of this, the nth power of a matrix, where n should be a positive integer, is just the A matrix multiplied together by itself n times. Of course, for this, A must be square matrix. So the important thing is that this is not the same as entry by entry power. This is a much longer process to multiply the matrix out by itself. Yeah, for example, if you have a 2 by 2 matrix, 5 minus 1, 2, 1, then A squared is the matrix multiplied by itself. So 5 minus 1, 2, 1 multiplied by 5 minus 1, 2, 1. And we have to do the regular matrix multiplication, which is not a short process. So we have the first row, first column, 25 minus 2, 23. First row, second column, minus 5, minus 1, that's minus 6. Second row, first column, 10, 2, 12. Second row, second column, minus 2, 1, minus 1. Another property is that if C is a real number, which means it's a scalar, then when you multiply with a matrix, a scalar product of the scalar multiplied B matrix, then you can factor out the C scalar from inside the matrix multiplication. We can only do that with scalars. If it was a matrix, we cannot do that because that would mean changing the order, and it's not possible in general to change the order of multiplication. We have some special matrices. We have the identity matrix denoted by capital I, where you have ones in the diagonal and 0 everywhere else. And the reason why it's called identity matrix is now more clear than before, because if you multiply together A and the identity matrix, you are left with the A matrix again. And you would have to do this actually to see it, that this is really what happens. The other special matrix is the 0 matrix with every element 0. And the important thing about this is that if you multiply a matrix with a 0 matrix, of course it has to be the right size of the 0 matrix. But then if it's the right size, then the multiplication is well-defined and equals to the 0 matrix of whatever size comes out from multiplication. Here are some examples for different multiplication. We have a 2 by 3 matrix and another 2 by 3 matrix. So notice that A times B is undefined because 3 and 2, these inner dimensions, do not match up. And b times a is also undefined because that would be a 2 by 3 multiplied by a 2 by 3. So again, the 3 and 2 wouldn't match. But if you calculate the transpose of the B matrix, what happens is that you interchange the rows and the columns. So the first row, 1, 2, 3, becomes the first column, 1, 2, 3, and the second column becomes the second row becomes the second column. And this way we get, from a 2 by 3 matrix, we get a 3 by 2 matrix. And the nice thing about this is that, for example, we can multiply the 2 by 3 A matrix with a 3 by 2 B transpose matrix, because then these inner dimensions match, and the result should be 2 by 2. And the way we calculate it is that first row, first column, 3 minus 3 is 0. That's the 1, 1 entry. Then the first row, second column is the 1, 2 entry, which is 15 and minus 2, 13. Then the 2, 1 entry is the second row multiplied by the second column. It's 2 plus 8, 10 minus 6 is 4. And finally, the 2, 2 entry from the second row, second column is 10 minus 4 minus 4. So it's 10 minus 8, which is 2. Next topic in this section is the matrix inverses. The definition of the inverse of an n by n square matrix is the matrix denoted by a to the negative 1, but it's not really a power. And for this matrix, what has to hold is that a times a inverse equals a inverse times a, and that equals to the identity matrix. So the inverse matrix, when you multiply it with the original matrix, should give you the identity matrix. It doesn't matter which side you are multiplying with. Not all matrices are invertible, or not all matrices have inverse. If A has inverse, then we call this an invertible matrix. And if the inverse exists, then it's unique. You cannot have two different inverses for the same matrix. Notice that in the definition, I require to have a square matrix, n by n square matrix. This is not actually a general requirement. It's possible to have inverse defined for a rectangular matrix, not a square one. And then we would have to talk about left and right inverse. Here, both of them are the same, both from the left and from the right. But if it's a rectangular matrix, then that's not the case. We would have to separately define left and right inverse, but we will not cover this in this class. There is no need for this. Some properties of the inverse: if you want to take the inverse of a product, you can take it factor by factor, but you have to change the order. Very important. You have to change the order when you take the inverse factor by factor. And of course, if some of the inverses do not exist here, then the whole inequality doesn't make sense. So this holds only if all inverses exist in this formula. We have general theorem about when a matrix is invertible. This is the case if and only if it is non-singular, which means that the homogeneous system has only the unique zero solution. So writing it down in a more compact way, AX equals 0 if and only if X is 0. So if you remember how we got unique solution for the homogeneous system, we had to do the reduced row echelon form, and then you get a unique solution if you get the identity matrix from here. So another way to write this theorem is that a matrix is invertible if and only if its reduced echelon form is the identity matrix. Now, here is a process for calculating the inverse matrix. You have to put together the augmented matrix where, in addition to A, you don't have just a right-hand side vector, you have a whole matrix, the identity matrix on the right-hand side. Then we have to row reduce this augmented matrix. And you have to pay attention because this right-hand side is quite big now, so you have to do everything on both sides while you are row reducing it. So if the A matrix is invertible, then you get at one point the identity matrix on the left-hand side as a reduced row echelon form. And then what happens is that kind of magically what you have on the right-hand side is the inverse of the matrix. And that's how you solve the problem to get the inverse. Now, there are other methods, especially for small matrices. There are other methods that you might have seen. Very important, you must use this process with the reduced row echelon form. Yeah? The whole semester we are using reduced row echelon form, and we will continue using it even for calculating the inverse matrix. You must use this even if you know some other methods, because actually that's the general formula. So for smaller matrices, there are some other formulas and also some theoretical reasons you might want to consider some other formula, but for our course, for practical purposes, this is the process. Here is an example. Here's a matrix A. It's a 3 by 3 matrix, so it's a square matrix. And we want to calculate its inverse. We put together A and the identity matrix into a big augmented matrix. And then we start row reducing it, which is kind of a long process. You have to try to do it fast, but also precisely. And you are allowed to do all the row operations we did before. For example, if you like this one here, because you want to have a pivot, which is 1, you want to move it to the first row. So what you can do is interchange the first and the third row to get this new matrix. So with 1 in the first pivot, 1, 1 entry, then the next step is to make the entries under it 0. So the new second row is the second row plus 3 times row 1, and the new third row is the third row plus minus 2 times the first row. And then we get this next matrix. I did this quickly, you have to check. By the way, I did several mistakes while doing this because it's just a lot of numbers, but this is it. So you have to practice it in order to get better with it. After we make this entry 0, then we go to the second row, second column, and we choose this as a pivot. And then we make, well, the entry under it is already 0, so actually we don't have to do anything in this step. So we go to the next row, third row, and the third column. There we have a last pivot, and now from here we are going backward, up, and we make the entries above it 0. So for this, what we need is that the new second row is the second row plus 2 times the third row. And same thing with the first row, it's the first row plus 2 times the third row to make minus 2 cancelled by plus 2. Then we get this matrix. Don't forget to do the multiplication and additions on the right-hand side also, the augmented part. So we got the zeros there. This is what we wanted. The next thing is going backward, now up. We want to make this 1 by multiplying the second row by minus 1. So we get this 0, 1, 0, minus 2, minus 1, 1. And then from here we go up to make the minus 2 disappear by adding to the first row 2 times the second row. And then we get Also from the right hand side we get 2 times the second row, minus 4 plus 2, that's minus 2, minus 2 plus 0, minus 2, and 2 minus 3 minus 1. And by this time then we get on the left hand side the identity matrix. So the process says that in this case, once you have this, whatever you have on the right hand side, that's the inverse of the A matrix. So you just have to read it from here. We can also check that this is correct, and I did it myself, and then I discovered that it wasn't correct, so I had to go back and figure out where I made a mistake. So make sure that you check your answer. You are also practicing matrix multiplication at the same time. So multiplying together the two matrices, we have to get the identity matrix, because that's the definition of the matrix inverse. There are a few homework assignments where you have to find out if a matrix is invertible or not. Actually, the way to find it out is that you try to find the matrix inverse. And if you get the identity matrix here, that means that the inverse is on the right. If you don't get the identity matrix as a reduced echelon form, that means that the matrix is not invertible. But that's the way to figure out if it's invertible or not. You try to determine the inverse. There is some theoretical argument here. If you have this AX equals B linear system, then actually you can multiply this with the matrix from the left, the matrix inverse from the left, A inverse, and that creates the identity matrix here with X, which is then just X, and you also have to multiply from the left with the A matrix inverse, the right hand side, and you get A inverse B. So this is another way to find the solution of a linear system, that you first calculate the inverse and then you multiply from the left the B vector, the right hand side vector, with this inverse. So this can be used in theory, but in practice actually this is a longer process, because by the time you get the A inverse using this reduced row echelon form, by that time you also solve the system, since that's also a reduced row echelon form using Gauss-Jordan elimination. So actually this is faster, because calculating the A matrix inverse and then multiplying, that's extra operation, which we don't want to do, especially if we have to solve a huge system, even with computer. So even when the homework says that you should calculate first the matrix inverse, actually I don't really care about that. You can just calculate the solution of the linear system using the Gauss-Jordan elimination, because it's faster. But in some cases, the problem is asking for the A inverse. You are forced to calculate it. And then if you do that by the same token, you can also just multiply out A inverse B to get the X solution vector. Small comment about block matrices. These are matrices put together from matrices. So A is a matrix, 0 might be a 0 matrix, 0 is a 0 matrix here also, and B is a matrix. Of course, you have to be careful what the sizes are, so the number of columns and the rows should line up nicely in these matrices, in the big matrix. The interesting case is when A and B are square matrices and invertible matrices. What happens then is that you don't have to go through the whole inversion process for the huge C matrix. If you want to calculate the C inverse, you could just calculate the inverse of A and the inverse of B and replace A and B with them. And that would be the inverse of the C matrix too. Yeah, here is an example. C is this 4x4 matrix, 1, 1, 1, 2. Then in this lower part, -1, -2, -3, -7. So this is a 4x4 matrix, which looks like huge. And if you want to calculate then the inverse of this using this reduced row echelon form process, then you would have to augment it with the big 4x4 identity matrix next to it. So that would be a lot of work, a lot of unnecessary writing of all these zeros. The idea is that because this is a block matrix, so that means that it has a block of a matrix here and another block here. What we can do is we can just calculate the inverses of these small matrices, 1, 1, 1, 2. So we augment it with the 1, 0, 0, 1 identity matrix. Then we do a reduced row echelon form. So we subtract from the second row or first row to get 0, 1, minus 1, 1. Then from there we go back and zero out the entry above the 2, 2 entry. So that means we subtract from the first row the second row. We get 1, 0, 2, and minus 1. And since we got the identity matrix here, that means this is the inverse of this small block. Similar way, we can calculate the inverse of this other small block, 2x2 block, minus 1, minus 2, minus 3, minus 7, augmented by the 2x2 identity matrix. Then reduce row echelon form. And once you get the identity matrix here, what's on the right hand side is the inverse of this block. And then the C inverse matrix is just put together from the inverses of these blocks and the zero matrices. Another thing we can do now is we can solve matrix equations. For example, AX plus B equals CX. A, B, C are given, and we want to solve for the X matrix. So the way we do it is we rearrange the equation. We subtract, for example, A times X from both sides to get B equals CX minus AX. Then we can factor out X on the right. It's important that because X is multiplying from the right, we have to factor it on the right. There is no commutativity, so we have to get the right factors on the right. Then from here, what we see is that well, we can switch the two sides around, because usually the unknown thing that we denote by X is on the left-hand side. So then to get X from here, we multiply from the left. So I wrote this on the left. We multiply with the inverse of C minus A on the left. And since the result of this multiplication is the identity matrix, and the identity times X is the X matrix, that means that if you also do this multiplication on the right, you get that X equals to C minus A inverse times B. Don't forget, left and right multiplication are different, so you have to factor out things multiplying on the right to the right. And also, if you want to cancel something with its inverse, you have to multiply on the right side, in this case, the left-hand side. So this is it. Matrix multiplication and matrix inverse.